Welcome to the demonstration of our design. This is just an overview of our whole prototype system. As you can see on the right there, mounted on the black baseboard, that is our prototype. So it has two solar panels, as you can see. The little one on the left there, that's our input sensor. The big one on the right is our output system model. For a full-scale system, it would be a whole solar farm of solar panels or several solar panels. And so the purpose of our project is to track the sunlight during the day to maximize the power output from our large solar panels to provide more efficiency for the resource. So we're just using a lamp, as you can see here, our lamp. We're just using that to model the sunlight source for our prototype demonstration purposes. And so the connections to our system, on the left here we have a power supply, just a regulated power supply, and we can turn it on. Just a regular power supply, approximately 12 volts to drive our system. So now I'll just take you through a quick look at each of the subsystems for our system, and then I'll talk about them in more detail just to give you a general overview of how our system functions. So the first part is the input system, which you can see here. As you can see, our sensor is a small solar panel. So what this system does is it will scan through 180 degrees of motion, and it'll find the angle at which there is most light flux incident to the input sensor, and then it'll send that signal to our large output for the large panel to track the light source. And then that input system connects to our microcontroller, which is in our case is an Arduino Uno. As you can see here, we actually have a shield. This is a prototyping shield just to protect our actual microcontroller from static discharge and to provide some extra input and output pins. As you can see, we have a lot of control wires coming off of it, which I will describe shortly what each of them does. So underneath here, this is the actual Arduino. This is the computer connection. That's the power connection here. See, that's our 9-volt battery power source. And part of the input system is also this digital display. As you can see, it has 4 wires coming off of it: the white, purple, blue, and green. The white and purple wires are wires that connect to the microcontroller to send the numerical signal to the display, and the other 2 wires are just power. So the next part of our system is the output system. This is our relay, which relays the low voltage power from the microcontroller to a control signal to our DC linear actuator. You can see here it's a geared linear actuator, and it turns circular motion into the movement of the shaft up and down. And our output system is this frame, steel frame, mounted onto the black baseboard, as you can see here. So now I'll just go into a little bit more detail of each of the systems, starting with the input system. I kind of went into some detail which I didn't mean to, but I'll go into more detail now. So this is our input system. It's made out of aluminum, which we hand fabricated. We cut the lengths of aluminum based on a sketch design that we did. And their pieces are connected with these elbow brackets. They're screwed right in. So as I mentioned earlier, this is our input sensor, the solar panel. It's mounted to a shaft, steel shaft, which is mounted to bush bearings, which are mounted to the aluminum frame with screws. As you can see, the shaft is coupled to a servo motor, 5-volt DC servo motor with a shaft coupler. This is the shaft coupler, 8mm to 12mm shaft coupler. And the servo motor is mounted to our aluminum frame with a custom bracket we built here. These are the power lines for the servo motor. Power and control. The servo motor actually has a built-in controller. I believe it's a PID controller, so it's all we have to do is send one control wire to the Arduino for control of the position of the motor, which is what we use to track the sunlight, or the light source in our case. As you can see, the two power cables here for the servo motor go into power supply from the Arduino, so it's actually fed straight from the Arduino because it has such a low power demand. And the orange wire here, that's the control wire for the servo motor. And as I mentioned earlier, the LED display, which tracks the millivolt voltage coming out of the input solar panel here. So I described those cable connections prior, two digital inputs to the LED display from our microcontroller, and it's also fed power straight from the microcontroller. So the Arduino Uno has a regulated 5-volt output, which is what's being used to power both the servo motor and the LED display because they have such a low power demand. And obviously the base power supply to the microcontroller is the 9-volt battery here. So if we look at our input sensor, which is mounted on our hardware that I described, it has two cables coming off of it. These are analog signals from the DC solar panel. So the white cable is analog plus signal, and the black cable is just ground. So if we follow these connections, they're zip tied to our frame there. And the analog input, the white here, it's a little hard to see there, it's fed into an analog input into our microcontroller, and the black cable is just fed into the ground for reference. So I can actually give you a demo of just the input system here. If I just move the lamp, as you can see, I'll position it here. And if I flick it on, our input sensor should track the lamp source. So I'll just power it up. And keep your eye on the LED display, which will display the millivolt output from the input panel as it's scanning. It should start shortly. There's a delay programmed in to help with setup. So as you can see, it found the millivolts. I believe the highest was 41 something. So at the end of its scan, it goes back to the maximum power point position, which is what was desired. So for our system, we programmed in a 126-degree range of motion based on the limitations with our output system. And for our purposes, we believe this is sufficient since the sunlight during a day doesn't really extend much past that angular limit, and if it does, the output is not very strong. So that's our input system. And now if we move on to a description of our output system, I'll start from the microcontroller. We have two control wires here, which are fed into a DC power relay, or an H-bridge circuit. So this is used to change the low voltage control signal from our Arduino into a higher voltage, not very high in this case, 12 volts as I mentioned earlier. These are the power cords to our DC linear actuator. So that is our relay circuit, as I mentioned, and these are the power supply. These are some other connections, sorry, to our DC relay. The purple wire here is connected to our power supply plus, which is our 12-volt power supply. The black cable here is connected to our power supply minus, which is ground. And we also have a green wire here, which is also a ground wire, which feeds into our microcontroller ground for proper operation of the logical output to our relay board controller, and there's an additional 5-volt regulated output. So the H-bridge circuit actually produces a 5-volt regulated output. And there's no use of this in our system. I just use it to reset the actuator position, because this 5-volt output, we can touch it to these pins, which are the logical control pins, and we can cause motion of the actuator. And obviously, as I mentioned earlier, the plus and minus power, DC power to our linear actuator here. So the circuit board switches the power to these terminals based on the logic going into these two cables. And I'll just give you a quick look at the nameplate there for the linear actuator. It's 12 volt, 1500 Newton push and pull, slow speed, 5.7 millimeters per second max, and 400 millimeters, so that's 16 inches stroke length. That's what we used for our system. So the 1500 newtons obviously provides plenty of force for, not a very big load. So I'll just show you the operation of the actuator using the 5-volt logical that I described earlier. So I'll just remove these pins from the microcontroller. I'll flick on the power supply here. It's on. As you can see, our H-bridge lit up to let us know that it's on. So as I mentioned, this is a 5-volt output, and if I touch it to the pin here, you can hear the motor turn on. As you can see, it's moving up, and it's reached its final position. I'm sorry if you couldn't see it moving. It's a little hard to film and touch the wire to the connector at the same time. So now if I put these pins back into the microcontroller here, there we go. So our system was calibrated to start functioning when the arm was at the top position. So first I'll actually just describe the output system. I'm sorry, I forgot to do that. So the linear actuator is bolted into our baseboard here, as is our output system. As you can see, it's screwed in. Input system, sorry, it's screwed in. And our steel frame is bolted into the output frame also. It's all painted black. Took a lot of time and care painting and sanding it. And so our steel frame here, as you can see, it has a hinge which provides the axis of motion. As you saw, when the actuator goes up, tilts higher. As the actuator goes down, tilts lower, as you will see in our demo. So the actuator is connected to a metal bracket that we made here. Metal bracket. This is a thick industrial rope, and the rope is connected to our frame with another metal bracket. And as I mentioned, the movement of the shaft provides tilting to the output frame. And our output solar panel is also mounted to the frame. As you can see, it's bolted into the frame on 2 points. And another aspect of this frame is that we had to add a counterweight, as you can see there, just a steel counterweight, which is what provides a turning moment. So when the arm goes down, the counterweight will provide a moment and spin the system to provide tilting. If it didn't, then it wouldn't tilt. So we did need the counterweight for that. And we have a top bracket to provide stability to our system, so we didn't want to have two separate poles there. And there is these two stops. As you saw earlier, the motion of the arm stops when the frame touches the stop, and it's actually calibrated that way for the top at least. For the bottom stop, you can see there, it's another stop. It just provides stopping for the frame when the actuator is at the lowest position it should be at. And obviously the output to our solar panel here, just a cable which we have connected to our load center. Not a very complicated load center. You can see the blue and the yellow wire, plus and minus wire, just connected to a resistor for our purposes. And for testing, we connected a voltmeter across the resistor and an ammeter through the resistor to test different power outputs for our system to compare it to a stationary system. So that was the testing that we did to compare efficiency for a conventional versus new system. So I can now show the operation of our whole system at work.